A certain volleyball team has a mean height of 70 inches with a standard deviation of 4 inches. Assuming the heights are normally distributed, part A, what is the percentile rank of someone who is 5'6"? So here, percentile rank means what percentage of the data are less than or equal to 5'6". Okay, so that's what you're trying to find in this question. And in order to do that, you just calculate the z-score for 5'6", and then you look up the area under the standard normal curve to the left of that z-score. So it's actually like really straightforward. So we're going to use the z-score formula. So this is the regular formula, not the one for the mean. So x minus mu divided by sigma. Okay, so the data value here is for this height, 5'6". Now, I think we're going to have to convert that to inches because these other two are in inches, the mean and the standard deviation. So 5'6" in inches, 5 foot is 60, and so that'll be 66. So this will be 66 for the data value, 70 is for the mean, mu, and then the standard deviation is 4. So actually, I think I can do this one without a calculator. So on the top we have -4, and the bottom is 4. So this is -1. And then for the 2 decimal places, you can put zeros since it's -1 exactly. All right, then you're going to go to your table, and you're going to look up the z-score of -1.0. Okay, so that's right here. And then for the second decimal place along the top, you want the one that's both zeros. Okay, so we're looking at the last column here. So the CDF cumulative distribution function for the z value of -1 is 0.1587. Okay, so CDF of this z-score is 0.1587, which is 15.87%. Okay, so that is the percentile rank. That's the percentage of volleyball players that would be less than or equal to this height of 5'6". All right, so now the other kind of question is percentile. So the 10th percentile, the meaning of this is the height that is greater than or equal to 10% of the players. Okay, so like the 15.87th percentile would have been this height of 5'6", and now we're looking for which height would be greater than or equal to 10% of the players, or to say it another way, 10% of the players would have a height less than or equal to the 10th percentile. Okay. All right, so the way you do this is backwards of what we just did on part A. So you want to get 10% for the CDF. So you're going to do a reverse lookup on that table of values for the one that gives you 10% area. And then you figure out what z-score gives you that. And then you convert the z-score into a data value by using the formula, the other version of the z-score formula. This one, x equals mu plus z sigma. Okay. So let me show you how to do that. Oops, I wanted to make that blue. Okay, so we're looking for what z-score has CDF equal to 0.1000 or as close as possible. Okay, so we're going to do the reverse lookup in this table here, and I'm looking for 0.1000 over here somewhere. So let's see, how close can we get? Oh, I think this is pretty close. Yeah, it's closer than the ones on either side of it here. So 0.1003 is the closest, and that is for a z-score of -1.28. So -1.28. Okay, so CDF of -1.28 has an area of 0.1003. Okay, and now you want to convert that z value or z-score to a data value using this formula, x equals mu plus z sigma. Okay, so mu is still 70 inches, and then we're doing -1.28 for z, and sigma is still 4 inches. Okay, so you put all that in a calculator, and I got 64.88. Okay, which is, if you want to go back to feet and inches, that would be 5 foot 4.88 inches. Oops, 4.88. Or you can just leave it as 64.88. All right, the next question is very similar. We're just doing 80th percentile instead of 10th percentile. So here we want to know what Z has a CDF of approximately 0.8000. Okay, and so we're going to do the reverse lookup again, and now I'm looking for 0.800, so around here somewhere. Let's see. Oh, I think that looks like the closest one. Yeah, it's off by 5 10,000ths. This is off by 23 10,000ths, so I think this one is closer. All right, and that's going to correspond to 0.8. So I'm looking over here now, 0.84. So 0.84. Okay, so CDF of 0.84 is 0.7995. Okay, so now convert to X to a data value with the formula. So X equals mu plus Z sigma. Okay, and I'm putting in 70 for mu again. I'm putting in 0.84 for Z, and then sigma is still 4. And put that in a calculator and get 73.36. Okay, which is, I think, 6 foot 1.36. I like to convert them back to feet and inches just to see if I got like a crazy height. You should get something that's not too unbelievable. All right, if you get like 9 feet tall or something, then you probably did something wrong. All right, why won't it indent properly? Okay, so moving on to number 2, it's pretty much the same problem, just different numbers. So a certain school has a mean GPA of 3.3 with a standard deviation of 0.5. Assuming GPAs are normally distributed, what is the percentile rank, and then what's the 25th percentile and the 90th percentile? Okay, so just to remind you, this means the percentage of GPAs that a 3.5 is greater than or equal to, or the percentage that are less than or equal to a 3.5, so depending on what perspective you look at it from. Okay, so for this we just convert 3.5 to a z-score and then figure out the area to the left of that z-score. So convert 3.5 to a z-score. All right, so here is our z-score formula, x minus mu over sigma. Okay, so x is the data value, that's 3.5. Mu is the mean, it's m for mean, so that's a 3.3. Sigma is standard deviation, s for standard deviation, so that's 0.5. All right, so top first is going to give us 0.2, divide by 0.5, and put that in a calculator, get 0.4. All right, so it's 0.4 exactly. You can put a 0 on the end for the second decimal place when you go to look it up. All right, and so we need CDF value, the area to the left of that. And get my table out. So we're doing 0.4 for the z-score, 0.40. So that's going to be 0.4, and then the 0 is up here. Okay, so we're looking at this entry, 0.6554. So 0.6554, that's 65.54%, since those areas under the curve are percentages in decimal form. All right, so 65.54% of the students at this school would have a GPA less than or equal to 3.5. Or to say it the other way around, a 3.5 GPA would be greater than or equal to 65.54% of the other students' GPAs. Okay, so for 25th percentile, okay, so we are looking for the GPA that has 25% of the other GPAs less than or equal to it. So it's like the reverse of this part A, doing everything backwards. Instead of getting a CDF, we start with a CDF of 25%. Then we look up the Z value. Then we convert the Z value back to an X. Okay, so we want Z, we want Z with a CDF of 0.2500, as close as possible, 25%. Okay, so let's do the reverse lookup. For 25%, should be around here somewhere. I think these two are the closest. The one on the left is off by 17 10,000ths. The one on the right is off by 14 10,000ths. So either one of those is fine, honestly. This one's just slightly closer. So I'll go with that one. All right, so that's for negative 0.67. So negative 0.67. Okay. So we have CDF of negative 0.67. And that gave us, what was it again? 2514. Okay. 0.2514. All right, that's as close as we can get. So we convert to X using this formula, mu plus Z sigma. So mu is, boop, 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 where did it go? 3.3, that's the mean. Z is negative 0.67. And sigma is 0.5. Okay, so make sure if you're on a 4-function calculator, you do the multiplication first. That's your order of operations, P-E-M-D-A-S, PEMDAS, right? So multiplication is first before addition. All right, if you're on a scientific or graphing calculator, you can just type it all in on one line. So I'm getting 2.965. All right. And that is less than the mean, and we got a negative Z-score, so that makes sense. It should be less than the mean. All right, so that's it for that question. And then the last one here, part C, is very similar. So we want a Z-score with a CDF of 0.9, as close as possible to 0.9. So we're going to do a reverse lookup for 0.9. Let's see, should be around here somewhere. These two are the closest, and the one on the left is a little bit closer, so 0.8997. And that corresponds to 1.28. Okay. So CDF of 1.28 is 0.8997. After a while, these Z-scores start to like be kind of memorable, I guess. If you were really obsessed with Z-scores, I guess you could kind of memorize some of these common ones. So this is pretty close. All right, anyway, I digress. All right, so that's as close as we can get to 0.9. And then we're going to convert Z to X using this formula. So mu plus Z sigma. So mu is still 3.3, Z is 1.28, and sigma is still 0.5. And we're going to put that in a calculator. And I got 3.94. Okay. All right, that's it for number 2. So number 3, exactly the same. Same 3 questions, just now we're doing chocolate chip cookies. So a commercial bakery produces chocolate chip cookies for sale. For quality assurance purposes, statistics about the cookies are checked. The mean cookie weight is 2.5 ounces with standard deviation of 0.2 ounces. Assuming the cookie weights are normally distributed, and we have the same 3 questions again, percentile rank, percentile, percentile. Okay, so for percentile rank, this is the percentage of cookies that weigh less than or equal to 3 ounces. So we're going to calculate this by getting the Z-score. So X minus mu over sigma. And then we will look up the CDF for that Z-score. Okay, so 3 ounces is our data value. Our mean is said to be 2.5 in the problem. And then standard deviation is 0.2. Okay. let's see, I think I can do this one myself. So this is 0.5 on the top, 0.2 on the bottom. So this should be 2.5 for the z-score. And we can put a 0 after that for the purposes of looking it up in the table. All right, then we're going to look up this z-score in the table, see how much area is to its left. Okay, so 2.5, here's 2.5, and then for the second decimal place, I want the one in the left column. Okay, so I'm going to have 9938, 0.9938. So 99.38%. So if we find a cookie that weighs 3 ounces, it's like a giant behemoth cookie because 99.38% of the other cookies would weigh less than or equal to that. Okay, now 15th percentile. So this is asking what weight has 15% of the cookies weigh less than or equal to it. All right, so for that, we're going to do a reverse lookup. So we want z with a CDF value of 0.15 or as close as possible. Okay, so we're looking for 0.15. 0.15. Okay, here I think are the closest ones. Okay, so the one on the left is off by 8 ten-thousandths. The one on the right is off by 15 ten-thousandths. So we'll go with the one on the left. So that's going to be z is going to be negative 1.0 and then negative 1.04. Okay, so negative 1.04, negative 1.04 gives us 0.1492, I think it was. All right, and then we're going to convert to an x value with this formula, mu plus z sigma. So mu is still 2.5, z is negative 1.04, and sigma is still 0.2. And we put that in a calculator and get 2.292. All right. And for the last part here, part C, so we want z with a CDF value of 0.75 or as close as possible. All right, so reverse lookup, let's see, 0.75, 0.75, somewhere around here. Yeah, these two are the closest. The one on the left is a little closer, so I'm going to use that. So that's for 0.67. Another familiar sounding value, right? So 0.67 will give us, oh God, can't tab well, sorry. 0.67 is going to give us 0.7486. 0.7486. All right. Okay, and we're going to convert that to a z, or sorry, an x value, data value, using mu plus z sigma. So that is going to give us, all right, mu is still cookie weight 2.5, z is 0.67, and then our sigma is still 0.2. Put that in a calculator, and we get 2.634. All right, so that's it for this type of question. So for the next type of question, we're being asked to make confidence intervals. So I'm going to bring the confidence interval table down to there. Okay, so now let's read the first confidence interval question. A random sample of 100 healthy adult humans found an average temperature of 98.4 degrees. There were no outliers. Assuming a population standard deviation of 0.75 degrees, make a 95% confidence interval for the average temperature of all humans. Write an interpretation statement explaining the meaning of your interval. Okay, so let's look through our table here. So variables are same ones that we've been using. Sigma is population standard deviation, m is the sample mean, and n is the sample size. So first thing for any of these procedures is check the assumptions, and here I've just said they're the same as for the one mean z-test, so let me go grab those and I will paste them there. Okay, so here they are. I'm not sure why some of them are sans serif and some have serifs, but anyway, it's those same three assumptions from the one mean, z-test, random sample, you have to know sigma, and then it's the thing about sample size and normal distribution. Okay, so we need to check all three of those. All right, so we're going to check assumptions first of all. Okay, so for the assumptions, assumption A is, was it a random sample? And so in the question here, it does say random sample. So this is yes. B is, do we know the population standard deviation? So it does say to assume right here that it's 0.75, so that's a yes. And then C is about sample size. So our sample size is 100. Okay, so looking up here, for sample sizes 30 and up, any distribution is okay as long as there are no outliers. Okay, so our sample size is 30 plus, and now about the outliers, it says there were no outliers. So we are good to proceed. All right, so assumptions, we're done with those. And let's go ahead and do number one in the procedure here. So number one, how did you get on the line number one? Okay, so number one is calculate alpha, and the formula is just 1 minus the decimal form of the confidence level. Okay, so I'm just gonna paste that down here. So alpha is going to be, let's see, what is our confidence level? So right here it says 95% confidence. Okay, so for our alpha, we're going to do 1 minus 0.95. Okay, so that's going to give us 0.05. All right, that's alpha. Number two is divide alpha by 2. All right, so very straightforward, just literally divide alpha by 2. Okay, so alpha over 2, 0.05 over 2, that is going to be 0.025. All right, number three, look up z sub alpha over 2. So now you know what alpha over 2 is. So you can put that in there. So this is going to be z sub 0.025. Now there is a way to look this up in the table, but if you forgot up how to do it, that's good because I don't want you to look it up in the table. I'm going to provide these z alpha values for you at the top in your info bank section right here. Okay, so you just need to pick the right one. So z sub 0.025 is 1.960. Okay, 1.960. So 1.960. All right. Step 4, calculate margin of error, and it has this formula. So E is the margin of error, and it's your z alpha over 2 value times sigma divided by square root of n. Okay. All right, so we're just going to plug all these things in. So our z alpha over 2 value, that's from right up here, 1.960. And then we're going to multiply that by this fraction, sigma on the top. So that's the population standard deviation, 0.75 degrees. And then on the bottom, we're putting square root of n, and that is the sample size. So the sample size in this problem was right here, 100. Okay. So be careful when you're doing this. If you're doing it with a 4-function calculator, be very careful. So you're going to do little steps by little steps with the simplification. So keep everything the same and just simplify one thing at a time. First, the square root there, square root of 100, I would do that first. So that's going to be 10. And then next, I would do this division right here, 0.75 over 10. Okay, so that's going to be 0.075. And then lastly, I would do this multiplication, the z alpha over 2 times whatever you have left here. So I'm getting 0.147. All right, so that is your margin of error. And then step 5 is calculate the confidence interval bounds. So the lower bound or the left side bound is your sample mean minus the margin of error. And then your upper or your right side is sample mean plus the margin of error. Okay, So we are going to do both of those. M minus E is going to be, so M is our sample mean, and that is right here, 98.4. So 98.4 minus 0.147. Put that in a calculator, and we get 98.253. And then for the upper bound, M plus E, same exact thing, just use plus. Put that in a calculator, and we should get 98.547. All right, so the interval is from 98.253 to 98.547. And last thing is the interpretation statement. You can just copy from here. So we can have blank % confidence, that's your percentage that's given in the question, okay? Or another way to say this is there is a whatever % probability that the population mean is between, and then you put those two numbers that you calculated, okay? So the interpretation is going to be, we can have 95% confidence that the population mean, so that in this case is average temperature for all healthy humans, human adults, is between, so the lower one 98.253 and the upper one 98.547. All right, so apparently it's not 98.6. Okay, so that's the whole procedure, and let's go ahead and do another one. Okay, so here I've just pasted kind of like the headings and the formulas from up above. Oh, I forgot to change the numbers. Okay, there we go. Just to make things a little bit faster. So let's read the question. A random sample of 25 ducks found that they quack 6 times per hour on average. Can you tell I just made this up? I get a little silly. There were no outliers. Assuming a population standard deviation of 4 quacks per hour, make a 90% confidence interval for the average number of quacks per hour of all ducks, and write an interpretation statement explaining the meaning of your interval. Okay, so first, check our assumptions. Do we have a random sample? It says random right there, so yes. Known population standard deviation, it says right here to assume that it is 4, so yes. And then the last thing is about sample size, so we have to be careful checking this one. So our sample size is 25, and so for 25 we need, okay, so that's going to be this one. Any distribution is okay as long as there are no outliers and the distribution is not extremely non-normal. Well, I don't know anything about it being extremely non-normal, but we are told that there are no outliers, so that should be okay. So it says that right here. All right. So proceeding along then, first we're going to calculate alpha. That's 1 minus the decimal form of the confidence level. So confidence level is right here, 90%. So we're going to do 1 minus 0.9. Oops, 0.9. So that's going to be 0.1. Next step is divide alpha in half. So 0.1 divided by 2 is going to be 0.05. Next step, look up z sub, and then it's whatever you got on the last step, alpha over 2. Okay, so z sub 0.05. So that's going to be at the top in the list of z alpha values. It is this one, 1.645. Okay, so 1.645. Next, we calculate the formula for the margin of error. So we're going to have our z value here, and then I'm just going to copy this for a second. All right, so sigma, we're told, is 4 quacks per hour. So I'll put 4 there, and then n is our sample size, so that's 25. All right, and put all that in a calculator. If you're doing it on a scientific or graphing, you can put it all on one line. If you're on a 4 function, go slowly, one thing at a time, starting with the square root. So you would want to do square root of 25 first, replace that with whatever it is. In this case, it's 5. And then I would do the fraction, simplify that next, 4 over 5. That's going to be 0.8. And then lastly, do the multiplication. So I'm getting 1.316. All right, so that's our margin of error. That is the value that we're going to add and subtract from the sample mean to get our confidence interval. So the sample mean here is 6 quacks per hour on average. Okay, so we're going to be doing 6 minus 1.316, and then 6 plus 1.316. So for the lower one, I'm getting 4.684, and for the upper one, it should be 7.316. Okay, so the interpretation here is we can have, so we were told to do 90%, so this is going to be 90%. 90% confidence that the population mean, which in this case is average number of quacks per hour of all ducks. A ridiculous thing, but okay. Average number of quacks per hour of all ducks is between, and then these are our two numbers that we got on number 5, 4.684 and 7.136. All right, and that is it. So let's do one more of that type. Okay, I've helped myself out by just pasting the starting parts here. All right, so last one, a random sample of 40 cats found an average tail length of 12 inches. Again, my brain just goes to ducks and cats and cookies and stuff. Assume that all tail lengths are normally distributed with a population standard deviation of 2 inches. Make an 80% confidence interval for the average tail length of all cats and write an interpretation statement explaining the meaning of your interval. Okay, so assumptions here. Do we have a random sample? Says that it is random right here. So yes, known population standard deviation says right here we should use 2 inches. And the last part about sample size, so we have 40, so that is 30 or more. So looking at the detailed guidelines here, any distribution is okay as long as no extreme outliers. And let's see what the question says. So it does say that they are normally distributed. So in that case, actually, it doesn't matter how small your sample size is. See, even if it's smaller than 15, normal approximation, if it's normally distributed approximately, then you're good to go. So for any sample size, actually, as long as it's normal distribution, that is fine. All right, so it's a subtle little point there. Normal distribution, so, okay. All right, so going through our steps here, alpha, 1 minus decimal form of the confidence level. Confidence level is 80%. So we're going to put 0.8 here, and that means we get 0.2 for alpha. Next, divide alpha in half, so that is going to be 0.2 over 2, which is 0.1. And, it should be whatever we got on the last step, alpha over 2 goes in the subscript by z here, so 0.1. So now I'm going to go to my z alpha values that were given at the top, and let's see, one of these should be for 0.1. Yep, right here, 0.1. So 1.282. 1.282. Okay. Next up, calculate the margin of error. So start with the z value that I got on the last part, 1.282. And then I have this fraction with sigma in the top. So population standard deviation, 2 inches. Oops. And then in the bottom goes, I'll just copy this little symbol here. So n is going to be 40, sample size, 40 cats. All right, so I'm going to simplify this one by one again, starting with the square root. I'm getting 6.235 approximately. Okay, so next I'm going to do 2 divided by that. And I'm getting 0.321. Okay, and then lastly for the multiplication, I'm getting 0.412, I believe. Was it 0.412? Yeah, okay. It's actually fairly far off. When I simplify one by one like that, I get 0.412. When I do all on one line, I'm getting 0.405, which is like a little bit far off. Well, it's off by 7 thousandths. I guess it's not that far off, but Yeah, so I will accept kind of like a range of answers, and I'm aware that intermediate rounding, I did a bunch of intermediate rounding here when I was simplifying, that can throw off the answer a bit. Okay, so anyway, next step is take the sample mean and add and subtract that margin of error. So sample mean here was this average tail length of 12 inches. So I'm going to be doing 12 minus, I'll just use the first one I got, 0.412. So that is 11.588, and then 12 plus 0.412 is going to be 12.412. All right, so for my interpretation statement, we can have blank percent confidence. This is going to be 80% coming from the question. Confidence that the population mean, which is average tail length of all cats, is between, and the two numbers that we just calculated, 11.588 and 12.412. All right. So that is it for these confidence interval type questions. And I'm going to stop the video here and resume in another part.